So, welcome to our session today. And yeah, sorry for the inconveniences here. So we really messed up. We destroyed the last session, but I'm very, very glad that you managed it so fast to hop into our new session. Yeah, regarding the topic, we've got the power over Ethernet, or PoE power. So I'm happy also to introduce our speaker today, Mohamed Al-Alami, who will do the presentation today and also answer your questions later on in the live Q&A. Then just some informations from my side in the beginning. You have the opportunity to ask us all your questions within the chat, so not by microphone, and we will later in the Q&A session hop into this. And yeah, if you also have any questions left, just email us at digital-v-days@we-online.com. And we will also share later on the recording of this session as well with the handout of the slides, so you will get all information. Of course, you also can find this session later on YouTube, so hopefully you will get all this information. So yeah, then I would say that's everything from my side in the beginning. I hope everything will work from now on, and I wish you an exciting webinar.
Hello, my name is Mohamed Al-Alami. I'm a field application engineer with Würth Elektronik. I have been with the company for 9 years, and I come from a power supply background. Today, I plan to talk about power over Ethernet. Okay, so here we go. Let's start off with looking at the agenda for today's presentation. So we start off by looking at the concept and the architecture for a PoE system. We'll just run through this fairly quickly. We look at the signal and the power flow side of things, and we'll also look at the PoE options for solutions, so the way that we can design a full system in terms of what an overview of the different alternative solutions that we have. We'll finish off with the key part of this presentation, which is to do with actually designing a PoE PD system, which is something that we have done for one of our customers. So we'll go through the design rationale and how we've actually achieved this. So concept and architecture, technology of passing power along the data lines using the Ethernet cable is something that has been around since around 2003, when the IEEE 802.3 standard sort of was put together. The idea behind this, of course, is as we are connecting all of these devices to Ethernet for data transfer, we might as well use that medium for transferring power as well, saving weight, cost, size, etc. So this slide is just to give you an overview of how the actual standard has progressed over the years. So we started off with the AF standard to give us the type 1 power transfer, which was limited to around 15 watts. And as the years have gone by, we had type 2 come through to increase power to 25 watts, 30 watts. And then we've recently had the .pt standard, which allows us power transfer up to 100 watts. Now, this also indicates the different types of devices now that we are connecting at the back end of this system, which now include motors, so they are a bit more power hungry, hence the increase in the power throughput requirements. How is power transferred? So this is just to give you a brief overview of the architecture of that system. So we start off with power sourcing equipment on the left-hand side. That is where the power is injected. It gets transferred through the Cat5 or Cat6 Ethernet cable along to 100-meter run, and then gets picked up on the power device side of things. That's your camera or IP phone, and that's where the power goes through a bridge rectifier. This is to ensure reverse polarity protection, so you can operate under both sides. If the power has been reversed for whatever reason on the PSE side, you can still continue to deliver power to the power device. This system here on the PD side of things also includes a DC-DC converter, which needs to be isolated to maintain the requirements of the IEEE standard, which indicates a functional isolation of 1500 volts. Now, depending on the applications, I know medical applications, for example, they require higher levels of isolation voltage, which needs to be achieved again via the DC-DC converter. One final aspect to mention out of this is this delivery of power from PSE to PD needs to be controlled, and that's what the PSE and the PD controller do. That's what I call the handshake. So the PSE will not deliver or release power to be delivered to the PD unless it is confident that this is the right type of PD with the right power level and so on. And this is captured in a variety of different signals, which we'll briefly look at in the next few slides. So how can we deliver or send power from PSE to PD? We can either use in this case here, what we're showing is a 10100 type system. We can either use the data pairs, as you can see there, or what we can also optionally use is the spare pairs. So that's what was called alternative A and alternative B in the IEEE standard, where you could only transfer on either or, and that's for a type 1 and a type 2 PD. That's when the standard only dictated that you can only deliver power over 2 pairs of Ethernet cables. And then came along the BT standard, which allowed us to handle more and higher levels of power. And now we're able to transfer power over all 4 pairs, as you can see in the picture here. And I'll finish off this section on concept and architecture by just showing you some of the solutions that us as Würth Elektronik are happy and capable of providing you on a system like this. So on the input side of things, we have got the discrete RJ45s, as well as the discrete LAN transformers or the integrated ones. We also have a wide range of EMC components that we can use on the front end over voltage protection in the form of transient voltage suppressors, as well as, of course, a wide range of filtering components for EMC, as well as for the power side of things, be it transformers or filter inductors or capacitors. Okay, PoE solutions and different options. So how can we implement a system, basically, is what this section is about. Before we do this, again, we'll just look a little bit on the handshake side of things, because we're predominantly today going to concentrate on the power side of things as opposed to the handshake. So with the handshake, and I'm really simplifying this today, there's something called a detection or signature resistor, which allows the PSE to identify the correct type of PD before releasing power. And then there is the classification side of things. That's what you see on this table here with the class number to identify the level of power that the PD requires for it to operate. So we've got the type, as we've shown at the beginning, types 1, 2, 3, and 4. And of course, we've got the classification as well. And this is usually done, and this is an extract out of an LT IC, just to give you an indication of how we set this from a classification, for example, a resistance point of view. So you can see that the PSE would be detecting the level of power required by the PD through these classification resistors. It actually sends a probe voltage and detects the current, and accordingly would identify this is a class 1, class 3, class 5, class 8 power device. Okay, so that's the handshake side of things. Let's look now into the different types of solutions that we can implement. All right, so the first option that we have is what I call the discrete solution. And the discrete solution is because you're using 2 separate ICs. One for this handshake, the detection and the classification side of things, or signature and classification as it's called. And the second one is for the regulation of the DC-DC, the isolated DC-DC we mentioned earlier. So with this type of solution, and I've got an example or a couple of examples shown here, you get the full flexibility in the sense that you have got 2 different ICs. In case you have an obsolescence or an end of life on one of them, it is easier for you to have to redesign part of the system as opposed to the entire system itself. So that gives you this a little bit more of a flexibility and freedom to do so. The integrated solution is number 2, and this is where those 2 ICs, basically the handshake and the controller for the DC-DC converter, are combined in one IC, with the example as shown here, with the LT4295. And this IC allows you to, of course, as it's 2-in-1, an easier layout and tracking, because anything that's in between now is already internal to the IC itself, naturally saving you size on the board as well. And of course, a very important aspect, which is key for us today, is the ability to add extra filtering, which is what you see on here. So I'll explain why this is important when we look at the third option. So the final and third option that we have is the module option. So with the module option, you have got everything on one board. So basically the handshake IC, the DC-DC controller, and the DC-DC itself, the converter itself, all on one board. Now, naturally, this has got a big lure because less parts, a smaller PCB area potentially, easier and better layout and tracking. It's all done for you, and faster time to market. However, two main issues remain. The one that I alluded to at the very outset, end of life or obsolescence. That means the entire system now has to be started from scratch. Potentially cost as well, because they might not be cheap, these modules. And finally, and most importantly, is the introduction of filtering, which is not going to be feasible when you have got a module like this. Where you see the arrow introduced here is where you can introduce input differential common mode filtering for this stage. You can't introduce filtering on the front end here. And the reason being for this is that the IEEE standard limits the amount of capacitance, inductance that you can put on that interface, because it does impact the signature, detection, etc., the classification, I should say, of the PD. So with that, as per the IEEE standard, and I mentioned clauses here out of the standard, you are limited in the amount of filtering that you can introduce, which can be an issue and a problematic one for that matter. So let's go into the final section and the important section of this presentation, which is actually the design example of a PoE power delivery device. As we will concentrate today on the power conversion side of things today, as opposed to the handshake, I thought I'll start off by just giving an overview of power converter design process. So naturally, the starting point with any power converter design is a requirement capture, so electrical, mechanical, thermal, dynamic. So all of these things are very important to try to naturally specify from the outset. From that point on, then you're able to select the type of topology, converter circuit that you need to realize these requirements. And from that point, you have got one of three options. Once you've identified that topology, you can design from the ground up, from basically an empty sheet of paper, do the full schematic capture, the full thermal analysis, the full design, functional testing, etc. On paper, which is an uphill struggle. It's quite it's a tough exercise, and you need to know your power supplies quite well. The second option, which is what we're seeing a lot of younger engineers are using nowadays, and to be honest with you, it's a fairly good process to follow as well, which is the use of an existing reference design, preferably something with an evaluation board, an evaluation kit. And that has to be done, though, with a massive caveat. You have to be very careful when you're doing or going down this line. And what we see is people wanting to just cut and paste, basically. That never works out. And this is why we have got this table of things that you must do and things that you need to watch out for, basically. So design specs may not match your design requirements. So the reference design is not necessarily set to fit precisely what your requirements are. Usually you don't have any EMI rejection or filtering on those reference designs or eval boards. And the reference designs also do not necessarily look at a wide range of input voltage loading conditions. So you'll need to adapt the reference design in simple words to your design requirements and make sure that both steady state and dynamic performance is maintained for your requirements. And that's one of the key aspects that you need to identify. for me, the final option, of course, is to go power module type. So you can buy an already made power converter. And for today, my example that I'm going to be designing is going to be based on an IC reference design. So I'm going to use the methodology that a lot of people tend to use nowadays. And so we start off with the design requirements captured from the customer. So we needed a 60 watt, so type 3, type 4 PD. Again, the IEEE 802.3.VT standard, 1500 volts functional isolation, input voltage 36 to 57, and the output voltage 12 volts at 5 amps, and the required efficiency was greater than 90%. Thermally, this was a key criteria for the customer. We needed to keep the temperature as low as possible, preferably less than 65 degrees. And the customer is quite aware of the EMI issues, having done this design in the past with other modules, and he was looking for also common and differential mode filtering for this filter. So there was quite a few different requirements that we needed to achieve. So the design architecture, as we started off putting the solution together, I've decided to go for the discrete solution. So one of the 3 options that we've mentioned at the beginning. So we'll go for 2 different ICs. I've decided to go also for synchronous rectified flyback topology, and that's to maintain the efficiency on the output side, given the 5 amps of current, and also for temperature requirements as well. This was going to be based on the on the LT3748 chipset from ADI. This is a primary side controller, and it also has a reference design evaluation board DC1961. So we have got a starting point or some hardware to try to use in order to verify the system. We've decided, based on the information that we had, that we needed a new transformer, again, from efficiency and temperature point of view, as you will see on the next few slides. And also to maintain that efficiency requirements, and looking now briefly at the handshake side of things, we decided to use an ideal FET bridge on the front end, so that we limit the dissipation and maximize the efficiency side of things. So the PDPSE handshake chipset that was used was the 4294, as you will see also later on. Front end design was based on this DC2583 reference design with evaluation board. So we had basically the full system put together if we wanted to straight away in order to do some testing. With the addition, of course, of input filtering, common as well as differential, and of course output filtering to limit the ripple to the 5% requirement. Okay. So we could just have picked up those 2 evaluation boards, stuck them in, and be done and dusted and not have to do any due diligence. But this goes totally against the purpose behind this presentation, or it would have been a very short presentation without us having to do any further work. So starting point in order to verify the actual reference design and see what modifications we needed to do, we ran the LT SPICE simulation based on whatever was provided by LT for this particular module. And accordingly, I've decided that naturally we needed a new transformer from an efficiency point of view. You will see why that is the case in a little bit. But we also needed to change the undervoltage lockout thresholds. We needed to look again at the dynamic response from an improvements point of view. We needed to redesign the clamp snubber to look at also a design for the current sense filter side of things. And as we mentioned, the implementation of the filtering from an EMI point of view. We've also looked at to improve efficiency at the main and the sync FETs to try to look for alternatives to those compared to what was in the reference design, again for a lower RDS on, I should say. So all of these are key aspects that we need to follow in order to try to optimize the design for the design requirements by the customer. And we finished off by actually modifying the evaluation board based on the above and creating also an initial prototype hardware to do the testing and the verification based on. And now here we can see the LT SPICE simulation file that is provided for the DC1961AF. And what you see is me circling the parts that needed to be modified on this design: the transformer, the snubber circuit, the filtering for the sense current, and of course the dynamic response, the input and output filtering. So all of these are areas where you need to look at in detail in order to make sure that the design is acceptable. So power transformer, we start off with the core of the design from a DC-DC converter point of view, a flyback. So the used transformer on this design or on this reference board was an EFD20 type transformer. And I've highlighted on this slide the inductance, the turns ratio, as well as the leakage inductance of the transformer as the key parameters. And I've also shown on the bottom of the slides the temperature rise on that transformer when it was tested under 48 volts in, 12 volts out, 5 amps. So we've got about 74 degrees worth of temperature on the transformer, which is higher than the customer's requirements. So we've decided to go for a bigger transformer, hence why we were looking for a new transformer, an EFD25, which is not massively bigger. It's only a few millimeters bigger in size and footprint. But with that, the key question is always when you're changing a transformer, is it going to work? So you look at key criteria like inductance or primary inductance. It's not too dissimilar. Same thing for the leakage. The turns ratio is a bit different, but you're still not sure as to whether this is going to be okay or not okay. Let's check though. Let's do this by calculation. Let's calculate if the transformer is going to be okay or not. This is difficult. Why is this difficult? Because the LT3748 chipset that we are using is a bound remote controller. So in other words, the switching frequency changes based on load and line conditions. So okay, so that's making things more complicated. How do I go about then finding out how to calculate my transformer, or whether my transformer is acceptable or not? So you've got one of two options. You can calculate the frequency of switching based on the calculation in the datasheet, which is what I have given here, or you can run the LT Spice simulation. And running the LT Spice simulation, as you can see here, will show you a switching frequency under full load conditions, minimum input voltage, worst case scenario, of around 82 kilohertz. So why is this number very important? In order to identify whether the transformer will saturate or not, it's important that you identify the worst case or lowest operating frequency or switching frequency for that transformer. So we've identified this using the LT Spice simulation very quickly and easily. This for me is the better way of going about it, but feel free to use the calculation, albeit within the datasheet itself, it says the calculation is not necessarily very accurate in order to try to identify that frequency. The next step is I use a calculator or a spreadsheet that I have created in order to assess the transformer. So this is the new transformer part number that you've got up at the top here with the inductance primary, turns ratio, saturation current, and I put in the electrical specification for our operating system. The switching frequency is down at the bottom here based on the simulation that we've done. And we have got a nice green peak current in the flyback, well below the saturation current of that transformer. So it gives us confidence about this. If you're not comfortable doing this, we have got a team from our sister division, Midcom, who are more than happy to assess the suitability of an alternative transformer at any time for you and give you a lot of this information and calculation. So that's the core part of the design done in terms of the transformer. And let's look around the other bits of the circuitry that we also need to assess. Next is the undervoltage lockout thresholds. We wanted to change the values of those for several reasons, and that's what I mentioned here under consider. So the values that were used originally didn't have a wide enough hysteresis. Now we've selected two new values for the two resistors here. That gives us a wider hysteresis level. Also gives us the ability to consider the drop across the diode bridge. Now in this case we used an ideal MOSFET type bridge, but you could very well be using a standard diode bridge on the front end. So that's also something to consider when you're coming to select this, because that's going to cause a higher voltage drop than an ideal bridge. And finally, of course, when you're coming to do the under voltage lockout, one thing to consider is this value here, because that's your minimum operating voltage now. So you need to make sure the transformer doesn't saturate, and under full power level that everything works okay under your minimum input voltage condition. Dynamic response. So when we ran this originally based on the recommended compensation capacitor and resistor, as you can see, 33 nans and 7.5K, we ended up with a horrendous response in terms of dynamic response. So when we put a step load, the voltage dropped or increased depending on which direction we went to by quite a few volts, let's just say. So we ended up changing those values. And how did we know all of this? We didn't test it naturally. What we did was simulate it to begin with. And we then tested it to see that, yes, we were getting a really bad dynamic response, which prompted us to change the values. As you can see here, now we've got a compensation resistor 25K, 10 nanofarads for CC. And that improved the dynamic response quite substantially. Instead of having a few milliseconds, let's say, of settling time and a few volts, quite a few volts of step response, now we're down to around less than a millisecond and a couple of volts of step response. So even with this, I think we still have got room for improvement on this front side of things. And as per the data sheet, you can go up to 50K. And I can't remember off the top of my head. Anything bigger than 1 nanofarads would be also okay, acceptable, in order to try to improve the dynamic performance of this. But this you can easily and simply do on the hardware itself as you go through. Another aspect that we also looked at is the snubber side of things, so trying to improve the snubber design. And as you can see here, we also did this by simulation and verified it in hardware, as you'll see later. So if you do not have the right values of resistors and capacitors to damp some of the ringing that you get as a result of the leakage inductance and the output capacitance of the FET, the leakage inductance of the transformer, I should say, which makes a massive difference. As you can see here in red is the damped response with a good RC snubber circuit. In blue is you have got very little damping of that response. And naturally, in line with this, of course, we need to clamp the lead edge spike at turnoff across the MOSFET, and that's where we use the WE-TVSP. It's one of our transient voltage suppressors that you can use in our product range. I've got hyperlinks, to these components, so feel free to go and check these devices as you go through. And one other filter as well that we've also included is just a simple RC filter to try to create the lead edge blanking effect. So basically, when you turn on the FET, you'll end up with a massive spike, which could cause mistriggering of the FET. And with that said, if you introduce a small filter here, you basically blank that initial spike from the IC. That covers the existing hardware side of things. Now we're talking about introducing extra hardware, which is the filtering from an EMI point of view, both differential as well as common, to cover both conducted as well as radiated. And this is the simulation that you see here of the overall filter that we have introduced. So I'm just going to go through briefly with the design rationale for the filtering. So we start off with the common mode filter. So we look at, first of all, the current that's being carried in the circuit or in the component. And we look at the switching frequencies that we may see. And accordingly, we can use Red Expert in order to select and optimize the selection of our common mode choke, which is the part number that has been used here. And I've included also a snapshot of the Red Expert impedance curve, which shows a fairly high insertion loss or impedance in those frequency ranges. We've done the simulation on LT Spice, and again, I have captured both the insertion loss at the 300 kilohertz as well as the 82 kilohertz, and you can see we've got ample attenuation at both frequencies. We do exactly the same thing for the input side, but from a differential point of view. So in this situation, we have got our inductor here, which is an XHMI series. Now, what we're having to remember here is the customer wanted fairly high efficiency and relatively small size. So that way, these were the criteria for using RedExpert to select this particular series of parts. The same concept was also followed for selecting the capacitors here, size, as well as, of course, maximizing insertion loss, having the highest capacitance that we can have, basically. And with this, we again tested at the two frequencies of interest, and again, we get a substantial amount of insertion loss at both frequencies for that filter. By the way, just to mention this as well, that filter has also got chip bead ferrites, which take us beyond the switching frequency into much higher frequencies. So that also gives us DM attenuation in the tens and hundreds of megahertz. And we finish off the filtering side of things with the output filter. Now, the output filter is mainly there for ripple rejection, because flybacks are not necessarily the cleanest when it comes to the output ripple. So we have introduced another LC filter that you can see here. And here it was a very big and important criteria for us to try to minimize the inductance value so that we got a very low R DC. So the DC resistance is small, so you get very little heating from the inductor, self-heating. And we can do that because the output is a relatively low voltage, so we can complement the low inductance with a high capacitance value, which is what we have done in this situation. I didn't want to show you another insertion loss in dBs. I'll show you the signal in terms of the ripple signal before the filter and the ripple signal in blue after the filter. And you can see the difference is quite substantial. 313 millivolts ripple compared to 9 millivolts ripple after the filtering. Next, we went on to implement all of these modifications that we have put together on the flyback board onto the evaluation board, because we've already got a starting point. So this is the original evaluation board. This is the modified one with the transformer, the undervoltage lockout, the dynamic the compensation loop. The only thing that this board didn't have on it was the EMI filtering. But then at that stage, we were just looking to ensure functional operation. So in terms of load line regulation, temperature rise, step response, and so on, and the voltage lockout thresholds. So we weren't keen at this time, naturally, on the EMI side of things until the actual prototype was built. Then we have got a more representative system to test the EMI side of things. And you can see also, just to finish this off, this is the handshake side of things with the ideal FET bridge that we also introduced as part of the system. So we've got as good a representation of the final system as we can. As a summary, based on the testing that we had done, regulation was absolutely fine across load and line conditions. We actually matched an efficiency of around 94% at max load and min VN. Thermally, the performance of the board was fantastic. Temperature on the board was around 42 degrees, as you probably have seen on the previous slide. And load transient was good, but I could see that we could also improve that further. The next step was to actually create the initial prototype hardware, and this is ongoing progress. We will be testing this in our Manchester office lab. So we'll do a bit of functional testing first, just to make sure that everything is working absolutely fine. So regulation, dynamic, thermal performance. But we will also be doing some conducted emissions debugging, some radiated investigations as well on the prototype. I'll finish off by showing just a couple of the slides with the final simulation that we've done for this system using LT Spice again. So that's the new transformer, the updated snubber circuit, the filter for the sense signal, on the voltage lockout, the compensation network as well changed, as well as the input and output filtering also included in the simulation. And you can see I've also included a few slides just showing you the transient response of the system, minimum load to full load. And I've also shown you a variety of different signals, the sense signal with and without the filtering, the drain source, which has been nicely damped, as you can see, the ringing on the front end, and the current as well, of course, in the main switch. Last slide, we've got quite a wide range of solutions and offerings from Würth. I've included a link to this. We will also have a set of links also available for you to click on during the day, so you can pick up a lot of these useful materials as well. I hope you've enjoyed this presentation, and I look forward to your questions. Thank you.
So, Mo, thank you very much for your presentation. And yeah, I'm happy to also see some more faces in this session. So it's very nice that you managed it to quickly register yourself. So if you have any questions, now we want to hop into the Q&A session. And yeah, we will dig in a little deeper and hopefully can answer all your questions. If we time-wise can't answer all your questions today, we will answer them later on via email. And if you have some questions left, then just email us at digital-v-days@we-online.com. So yeah, I hope we can start. So we are also, okay, I see Mo is coming also. So first question, we would start. Mo, how did you identify the changes needed to the reference design?
Good morning, Marcus. Good morning, everybody. Yes, good question. Yeah, that's you have to really look through the reference design to begin with, because that's your cornerstone for modifying any changes or identifying any differences that you need to do. So it's good if you are lucky enough for that reference design to just copy across, like I was saying earlier. But 9 times out of 10, there will need to be modifications. And one of the first things that we saw when we looked at the testing that was done on the evaluation board was that there was a high temperature on the case of the transformer. Now that automatically prompted the change of the transformer. And then the next step is you would be studying in a bit more detail your design requirements, your specification, input voltage, efficiency, ripple, and so on. And accordingly go back to the reference design and see what solutions have been implemented for filtering, for example, to reduce ripple, or what the under voltage lockout is as per the reference design, and modify these accordingly. But the point here is a reference design is very good starting point, but it's not the end game. The end game is you having to do some of this due diligence and identifying these as you go along. I hope that answers the question.
I hope so too, but I think so too as well. So thank you very much, Mo, for your question. Yeah, I also want to share the handout, so the slides you just saw with you. So hopefully you can see it right now. And yeah, you can directly download it, but we will also share this link as well with the recording later this week. So, okay, not waste too much time with this. Next question, Mo. The filtering introduced is for conducted emissions. How about radiated?
Okay, yeah, that's a good question. Actually, the filtering is for both conducted and radiated. I maybe concentrated more on the conducted side of things when I was talking about this at 80 kilohertz, sorry, and 300 kilohertz being the switching frequencies that you may encounter during steady state operation. But with the selection of things like chip bead ferrites, as well as the common mode choke that I'd selected for common mode insertion loss at the beginning, if you look at the bandwidth of both filters, you will see that this cuts very much into the radiated side of things, up to around 400-500 megahertz and beyond. The idea behind choosing a common mode choke in particular, because we know flybacks are notorious for common mode noise, is that that common mode choke has also got the Y capacitors. You might have noticed this on the schematic. So the common mode choke with the Y capacitors gives us insertion loss in the lower frequencies, which is the critical end of things, the conducted emissions. But the common mode choke and the caps as well will continue on to give us a fairly wide insertion loss up in the radiated emissions side of things as well. So we did cover both conducted as well as radiated for this filter.
Okay, Mo, thank you very much. Then let's hop into the next question. Is an isolate? Oh, I will also share it for you so you can see the question as well.
Yeah.
Is an isolating converter required, or can non-isolating converters also be suitable for power over Ethernet applications?
In most applications that I have come across, isolation is a requirement. Some, very few, that would not require direct isolation between primary and secondary. And the isolation, again, maintains the isolation of your discrete land transformer. Otherwise, you wouldn't need a discrete land transformer. Its main function is to give you that 1500 volts or 4 kV, depending on the applications that you have, of that level of isolation. But there are also some systems which also have a backup supply. So they're sometimes supplied from a 12 or a 24 volt supply on the side, where isolation might not necessarily be required, and you can just use a standard buck converter more likely. I would say, is some of the applications that I have come across. But maybe to just answer simply, most of the times you will require some form of an isolated converter, and it tends to be either a flyback or a forward converter.
Okay, thank you very much. Then I think, Mo, we have still time for at least one more question. Is the LT SPICE schematic shown before available for download?
Unfortunately, that's not available. That is something that that I've put together with our customer. But please do forward your email on to us. We are more than happy to discuss what your requirements are, and we can always see what we can support you with from this schematic point of view or otherwise. So that's not available in the public domain, that design yet.
Exactly. Okay, thank you very much, Mo. Then we still have time for the last question I can see right now. And if there are still more questions, just as Mo said, just contact us directly with email. So, yeah, okay, it's regarding the same issue, I think. Might we get links for your simulation that you already did? So can we save time with adjustment of our design? Yeah, so well, I think it's the same topic.
Sure. Yeah, I think it's just contact us directly, and we're more than happy. We've got a very experienced FAE team globally, and we all work LT SPICE predominantly as our simulation tool of choice, because the models for all our components are in there. And when you see the simulation that I've performed in LT SPICE, that simulation actually has got the actual model for the transformer, for the inductor, even for the capacitors, with things like DC bias effects as well on common mode chokes, on chip beat ferrites. So on chip beat ferrites, I shouldn't say common mode chokes. So with that, I think you will find you get a very good representation of the performance of the system. But yeah, please do contact us. We're more than happy to support.
Okay. So Mo, then thank you very much for your answers and your time today. And also thank you very much for your attention. I hope you enjoyed our session at our Digital V Days. And yeah, just one more word from my side. If you're interested in more sessions from us, we will quickly share also a link. Keep informed, maybe, yeah, register to another of our big sessions in this week. So yeah, thank you very much and have a great week. Bye.
Thank you, Marcus, and thank you, everybody. Enjoy your week.